Hello students, welcome back. In today's class, we will be discussing about transformers. Now transformer, as you already know, is a device based on the principle of mutual induction, which is used for converting large alternating current at low voltage into small current at high voltage and vice versa. So basically it is used for converting current at different voltage. So it is used for converting one level of current into another. The transformer which converts low voltage into high ones are called step-up transformers, while those which convert high voltage into lower ones are called step-down transformers. Transformers are used only in AC circuit, not in DC circuit. Okay, transformers which converts high voltage into low and vice versa is only used in AC circuit, alternating current circuits. It cannot be used in a DC circuit. Okay, now construction is there. As the diagram over here shows a transformer. This is a step-up transformer. Okay, a step-up transformer converts low voltage into higher voltages. That is the work of step-up transformer. So a simple transformer consists of two coils, the primary and the secondary. There is two coil, primary coil over here and secondary coil in the lower section, which are insulated from each other and wound on a common soft iron laminated core. This is a common iron inside laminated core. There is iron laminated properly, a layer of irons laminated properly, and primary and secondary coil are wrapped around it. One of the two coils have a smaller number of turns of thick isolated copper coils, while the other has a larger number of turns of thin isolated copper wire. So over here in the step up transformer, there are smaller number of turns in primary coils. These coils are thick isolated copper wire, while in the secondary coil, these are thin isolated copper wire and there are large number of turns. In a step-up transformer, the coil of thick copper wire having smaller number of turns is the primary coil, and the coil of thin wire having larger number of turns is the secondary wire. In a step-down transformer, the order is reversed. So there is the diagram of step-up and step-down. In the step-up primary coil, there are less number of turn, more number of turn in secondary coil, whereas in step-down, primary has got larger number of turn, in secondary it has got lesser number of turn. There is core material in the center. The core material is soft iron laminated. Okay, this is soft iron which is laminated. Now the theory of this part. The given source of EMF, say AC main, is always connected to the primary coil. You can see over here, this part is the AC main. Okay, this part is the AC main which is connected, main circuit is connected to the primary coil. Okay, when alternating current flows through the primary coil, then in each cycle of current, the core is magnetized. This core is magnetized once in one direction and once in opposite direction. Hence, an alternating magnetic flux is produced in the core. Since the secondary coil is also on the same core, the magnetic flux passing through it changes continuously due to repeated magnetization and demagnetization of this core. Therefore, by mutual induction, an alternating EMF of the same frequency is induced in the secondary coil. The induced EMF in the secondary coil depends upon the ratio of number of turns in the two coils. Suppose NP and NS are the number of turns. NP is the number of turns in primary, NS is the number of turns in secondary coil. Now let us assume that there is no leakage of magnetic flux, so that the same flux passes through each turn of the primary and secondary coil. and let phi be the magnetic flux linked with each turn of either coil at any instant. Then, by Faraday's electromagnetic law of induction, the EMF induced in primary coil, okay, EMF in primary, and E written with P. Okay, I've missed this out. This NP is number of turn in primary, NS is number of turn in secondary, phi B is the magnetic flux, EP is the induced EMF in the primary coil. By Faraday's law, it is number of turn in primary multiplied by change in flux over change in time. This is EMF in primary. And the induced EMF in secondary, ES will be minus NS del phi B by del T. Therefore, if you find the ratio of this one, therefore ES by EP is equals to, if you find the ratio, then what we get at the end is every common factor will get cancelled out, and we will be left out with only the factor that is NS and NP. Minus minus gets cancelled, del phi by del T get cancelled. Therefore, ES by EP is equals to NS by NP. If we consider the resistance of the primary circuit be negligible and there is no loss of energy in it. When current flows, we know that there is some sort of loss of energy due to some sort of resistance. But what we are considering is the resistance of the primary circuit be negligible. There is no loss of energy. Then the induced EMF in primary coil will be nearly equal to the applied voltage across its end. So if there is no loss of resistance, then ES will be equal to the voltage across secondary coil and EP will be equal to the voltage across primary coil. Therefore, Vs by Vp is equals to Es by Ep, which is again equals to Ns by Np. This is under ideal condition, which is equals to R. Now this R is called the transformation ratio. Okay, in step-up transformer, R is always greater than 1, whereas in a step-down transformer, R is always less than 1. Thus, voltage obtained across secondary coil by voltage across primary coil. Okay, I'll write it over here. Voltage across secondary coil divided by voltage across primary coil is equals to number of turn in secondary coil divided by number of turn in primary coil. Now if we consider current factor IP and IS, this is the IP is the current in primary coil, IS is the current in secondary coil at any instant, and the energy loss be 0. Okay, there is no energy loss while the current is IP and IS. Then the power associated, okay, the power in the secondary coil, that is power in secondary coil will be is equals to power in primary coil. So now the formula of power is equals to V into I. So this becomes power in secondary is V into I. Power in primary is V into I. From here, IP by IS is equals to VS by VP. This was is equals to NS by NP, which in turn was is equals to the transformation ratio. Now from here, what we can conclude is, thus when the voltage is step up, okay, when the voltage is step up, the current is considerably reduced in the same ratio, and vice versa. As the ratio of voltage and current is equal, so if voltage increases, current automatically will be reduced. Thus, the energy obtained from the secondary coil is equal to the energy given by the primary coil. Obviously, the transformer is not a generator of electricity. It only converts voltage from higher to lower factor. So you need to remember this equation of transformation ratio and the construction as well as theory of transformer. Now there are a few topics which is homework for you guys. You people will go through this by yourself, as in this topics there is no derivation, no calculation, and no diagrams as well. So only few points, 2 or 3 points from each topic you can write it down, not from the first topic. The first topic is alternating current generator or AC dynamo. This you have studied in class 10. Same thing, same diagram, same construction and same working. You can go through by yourself. Energy loss in transformer. There are 4 different types of energy losses. You can write any 3. Utility of transformer. Any 3 utility of transformer will do. And the 4th one is utility of alternating current in comparison to direct current. This is an important topic. It is given point wise in your book as well, so you can just write it down in your notebook. So with this we come to an end to this chapter. There are 3 numericals from ISC, so I'll do that to complete this chapter. Okay, I'll continue with the numericals, and with that the chapter that is alternating current will be over. The first question is from ISC. It is the electric main in the house is marked 220 volt. Okay, V electric main of voltage is 220 volt. 50 Hz is the frequency. Write down the equation of instantaneous voltage. The only variable in the equation should be T. So T can be variable, rest we have to change. So the equation for alternating voltage is V naught sine omega t. So in this equation only T can be variable, rest we need to find V naught and omega. So let us first of all find V naught. From the equation of VRMS is equals to V naught by under root 2. So if you use this formula, we can easily find V naught. So from here, V naught is equals to VRMS root 2, which is VRMS is 220 under root 2. So we have found the value of V naught. Now let us find omega. Omega is 2 pi f. So putting the value of f becomes 2 pi into 50, which is 100 pi. Okay, now ultimately what you have to do is have to substitute the value of omega and V naught in this equation. So it becomes V is equals to V naught is 220 over 2. Sign cannot be changed, sign will be sign only. Omega is 100 pi and T can be a variable. So ultimately this is the final equation of alternating voltage. Now another question is question number 62. I hope the question number doesn't matches with your book. Just match the question, okay, not the number. Question is, in an AC circuit, resistance is 40 ohm. Question number 62. Resistance is 40 ohm. Z, that is impedance, is 50 ohm. VRMS is equals to 200 volt. Okay, VRMS is 200 volt. Calculate the average power consumed over a full cycle. Hint is also given, but first of all we need to the formula is P is equals to I square into R. This is one of the formula of power. In place of I, we are writing IRMS. So first of all we need to find IRMS. IRMS is equals to current is equals to voltage divided by resistance. Not this resistance, but this impedance, which is also the resistance, that is Z. So V is 200 by Z is 50, which gives us 4 ampere. Now P is equals to IRMS square, which is 4 square into R is 40. So this gives 640 watt. This is for question number 62. Now there is another question just below that. The question is a resistance of 150 ohm. Okay, the resistance of 150 ohm and a capacitance of 15 microfarad are connected in series with an AC source. The peak value of current is 0.20 ampere. Calculate the average power consumed in the circuit. We need to find power in the circuit. If the capacitor is removed but the current is kept the same, what is the average power consumed in the resistor alone? Now, if you remove or keep the capacitance also, there is no power consumed by the capacitance. Okay, so it is only the power consumed by the resistance. So we'll only find the power consumed by the resistance. So these are the values given. So formula of P is equals to half V naught I naught. Okay, this is from LCR series circuit. Now V naught we don't have. Instead of V, what we are going to write is V is I into R, or I naught into R multiplied by I naught, which gives half I naught square into R. I naught is 0.20 square multiplied by 150. Do the calculation, your answer will be around 3 watt. So for the second part of the question is also the same answer, that is 3 watt, because capacitance doesn't make any difference. Now with this we come to an end to this chapter. In the next class we will be starting a new chapter, a new unit, that is electromagnetic waves. Okay, that's much for today. Thank you.